Okay, so I hope you already scan the QR code and submit the Google Forms. Has anyone, is everyone having trouble submit the Google Form? The links works, right? The links work. I haven't checked the QR code, so I hope the links work. Okay, we will start for today's class, continuing the chapter 12. So we have learned the introduction for the vectors, the vector itself, the dot product, cross product, okay? And now we will learn on the vectors in terms of line and plane, okay? The equation of line and plane on the vectors. Okay, so maybe before we start, let me write the subsections. This will be equations of lines and planes. Okay, so if we have a space coordinate at P0, a little bit blurred. Let me make it a little bit smaller, and then okay, maybe it's better. Okay, let's say we have this P0, the X, Y, and Z. So this is we call as our starting position, okay? And we have the vector position. We have vector position R0. So let R0 and R be the position vectors P0 and P. And of course, if you see the line, they are the vectors P and P0 is representing the OP, OP0 and OP in the vectors. If A or vectors A, okay, represents vectors P0P, okay, then we will have the vectors R equal vectors R0 plus the vectors A. Okay. So we can connect vectors to another vectors with some shifting through some vectors A in between of these two vectors. Okay. And then if we have, let me put the drawing here so we can see both of the figures. Okay, let me draw it like that. And then similarly, from the first figure, if we like to change the R0, the positions of R0, we change the direction. Okay. We'll see that the product or the results on the final vectors, they will result in different length. Okay. It depends on this we call T as in parametric. T equals 0, T greater 0, or T less than 0. So, since the vector A and vector V, let's say we have another vectors that the green one here. If you look on how the V and A, they are the parallel. They are parallel vectors, A and V. So let A and V are parallel. And we can exchange the positions of R0. Okay, we can exchange positions, and then there is scalar, which is t, such that the vector A is equal t multiplied with vector v. So we can also write the vectors R equal, and we can exchange A with T multiplied with the vector V. So each value of the scalar, this will determine how the positions will be, how the position of this P0 will be. So each value of t, this will be gives position vector. R of a point on the line L. And you will see that when t is negative, you will see that it will be going to be on the left side here. And when t is positive, it will be going to the right side of this line. And when t equals 0, this will exactly at those points. So we can imagine these equations when we are changing the e. We imagine that if we have this line, and imagine this is the first, the initial point when t equals 0. Maybe we are going to have to make it a negative. Okay? We are going to the left. When we are making it to the positive, we are going to the right. Okay? This is just an illustration, okay, on how we can visualize how the vector's position or position of the vectors looks like. And then, if we let this vectors be, okay, it has some direction. It has some direction in 3 dimensions. Let's say it has some numbers, right? Or maybe we can write the v. Okay, let component of vector v become a, b, c. Okay, to make some definitions. Okay. Then we have, if we multiply with the scalar t, then we have ta, tb, and tc. We can also write our vector r as x, y, z. Okay, and our r0, this is x0, y0, and z0. So we can rewrite our vectors r with each component. We can write with each component. So we can write x, y, z. And we can add each component of x, y, and z. So x0 plus ta, y0 plus tb, and z0 plus tc. Now we have a conditions that x is equal x0 plus ta, y is y0 plus tb, and z0 plus tc. Okay? Or maybe not ta, maybe at, maybe that will be better. Now this component of each x, y, and z, all these three is called the parametric equations. So we call this parametric equations for each component of line L. So we can break down our vectors from the general positions vectors into each component of x, y, and z. Okay. And we can say that A, B, and C is a sense of directions. Okay? It is to make sure that it goes the direction A for x-axis, the direction B for y-axis, and direction C for z-axis. And we can explore through what we call the vectors V. Can we imagine V is parallel vectors with the vectors R? Okay, let me give you illustrations how we can look on more practical approach. But maybe let me write the question first before we look on the graph. So example, find a vector equation and parametric equation. For the line that pass through five, 1, 3, and parallel to vector I plus 4j minus 2k. Now, okay, let's working on this example. This is simple question. Find the vector equation and parametric equation. So which means the vector equations means that the R that we are having in the general rule, the R, R0, and the EV, right? And the parametric equation, we need to find each x, y, and z in terms of parametric. And then the line pass through some point and parallel to the vector I plus 4j minus 2k. So parallel with the vectors means that you know the directions will be the same with this the second vector, which means we know the v the ABC from this vector. And the passing through point, we can treat this as our initial vector, the R0. So we can draw, for example, it has been drawn. Okay. If you want to draw, you can draw. So that's this point 513 as our initial position, okay, for the vector R0. And this will be the directions. Okay. Let's say this is the directions. So we can take the R0 as 5, 1, and 3. Okay. Or we can write as 5i plus j plus 3k. And we have v I plus 4j minus 2k. Now we can write our R. Let me take these vectors. We can add all this x-axis, y-axis, and z-axis, all this I, j, k. We can add, and don't forget to multiply this v with the parameter t. Okay, the parameter t, because we have the scalar t in our general formula that we need to define. So we need to multiply with t, which means that this should be t. Okay, multiply with t. So the vectors becomes 5 plus t and then 1 plus 4t for j and plus 3 minus 2t for k. Now we are looking at each component here. So this is the vector equations. Okay, so this is the vector equation. So vector equations, this R, and parametric. This will be x equal 5 plus t, y equal 1 plus 4t, and z will be 3 minus 2t. Okay, now I forgot to mention there are some additional information. Aside from this parametric equations, we can also rewrite this in terms of t. So we can rewrite this and becomes t is x minus x0 divided by a, or in terms of y, or in terms of z. And all the terms is equaling with t, right? So we can take these equations and make all the equations equal. And it's become x minus x0 divided by a, This is called the symmetric equations. And some notes, okay, or maybe just one note. What's happened if the directions, one of these directions, 0, maybe A 0 or B 0 or C 0, which means that we can take the, for example, if A is 0, so if A is 0, so the equations will be x equal x0, and the other two will be still equating and don't make substitution on this equation at 0 here. Make substitution at the very beginning. Okay, let me go for another example to show how we can have some line intersections. So the questions, find parametric and symmetric equations of the line that passes through points A, which is 2, 4, -3, and B. And the second follow-up questions, at what point does this line intersect the xy plane? So first you need to find the parametric and symmetric equations of the line passing through a point A and B. So we need to set up a vector from these 2 points, from point A and point B. We can set up AB or BA, depends on you. And the second follow-up question, at what point does this line intersect the xy plane? The xy plane, if you remember how we can take the plane, we need to set up one of the axes to be 0. For example, for xy plane, then we need to set up z is equal to 0. Right? So let take the vector AB and this becomes 3 minus 2 is 1, or maybe let me write one by one so you know where does it's come from. So 3 minus 2 minus 1 minus 4 and 1 minus 3, so plus 3. So this will be 1, negative 5, and 4. And let's make this line, because it's parallel to our line, okay? So we can take this AB and set this as our V. And we know that this is A, B, and C. Then we can set up X. Let's start from A. So this is 2 plus T. And Y is 4. So let's maybe make some assumptions here. So R0, we can set up this is 2, 4, and negative 3. So we know more structure. So 4 minus 5t and z minus 3 plus 4t. So we set up the parametric. And for the symmetric, we can set up solve for t. So we will have x minus 2 equal y minus 4 divided by negative 5 and z plus 3 divided by 4. Or if you want to complete with the equations, this is divided by 1. So this will be the symmetric one. Okay, at what point does this line intersect the xy plane? So if you remember, this is our space, z, x, and y. So let's take this xy as a plane here. So imagine that if we set up this as 3 dimensions, let me draw. If you set this xy plane here, right? This means that this is true when z is equal to 0, right? We have the xy plane. So we need to set up z equals 0. So we can set up this 0 and we get some parameter, right? Some certain parameter. And we are using those parameters to look on which point that we are going to have the intersection. Okay. So the line intersect xy plane when z is 0. So we know that 0. So we will have t is 3 over 4. Now using this parameter t, we will get x. 2 plus 3 over 4 is 11 over 4. And we will get y is 4 minus 5, 15 over 4. This will be 16 over 4. 16 minus 15 is 1 over 4. So we will get the line intersections is 11 over 4, 1 over 4, and 0. So the line is like at this point 11 over 4, 1 over 4, and 0. Or if you would like, you can also set up z equals 0 at this one. And we can equaling each y and x, and we still get the same number. And from this example, actually, we can set up some definitions or probably some methods. So if you look on A and B, if t is equal 0, then it's just this position vector of this A, if the R is right. If t equal 1, we will have the final result is B, the position vector of B. So actually, we have something called segment or line segment. So we can have a segmented line. Let me describe on the next page. Okay. So line segment of vectors AB you can describe in this parametric. This is where t is from 0 to 1. Or if you write in terms of vector equations, you can have so the line segment, it helps us to analyze, okay, not the entire line, but let's just take some segmented line and then observe within the t from 0 to 1. Okay. Because frequently we are just need some descriptions, not really the entire line. So we are just focused on the segment line. Because from the segment, you get the sense of the directions. You can get the sense of the initial position, and I think that's the first idea on how we can analyze the vectors. So we just need the segment line, the line segment, not the entire line, like from the start to finish, but just to see what's the directions. I think that's enough to observe vectors. So in general, line segment from position vector R0 to, let's say, R1, okay, given by or if you would like to look on more how we can get this 1 minus t, this is from R, okay, where the phi is actually R1 minus R0. So we can take this into R0 plus R1 minus R0 and t. Or we can write 1 minus t R0 plus t R1. Okay, another important keywords, okay, that's I think important in line. Okay, as I mentioned in the previous slides, we have first parallel. I think you know parallel means. The second that we did before, the intersections. So line can be parallel, they can be intersected, and the third option is we call the skew line. The skew means they are not intersecting and they are not parallel. Okay. So we will have at least three conditions for line. So first is parallel. Let's say this is parallel. So we call this parallel. Let's say this is intersect here. Okay. This is intersect. And the other one, let's say this is not intersecting, not parallel. Okay. Let's say this is a skew. Or maybe let me draw more clearly. Let's say draw like this, but this is not intersecting. Okay. So it's like maybe like this, and you will see that it's not touching. Okay? It's not crossing. To give you some practical approach to look on the skew lines, let me give you two lines, and then we'll see whether those two lines are skewed. Let me give you example, maybe here. Example. So let's say we have line 1. They have parametric equations x equal 1 plus t, y equal minus 2 plus 3t, and z equal 4 minus t. It's a line 1. Line 2, we will have x equal 2s. S is another parameter in this case. And y is 3 plus s. And z is minus 3 plus 4s. So of course, what we are going to do is we need to prove whether this is skew or not. From the parametric itself, if you look on the directions, this is 1, 3, and -1. So directions, let's say the directions on L1, so let's say V1 is 1, 3, and -1. And V2 is 2, 1, and 4. Because V1 is not the same as V2, then we know that this is not parallel, right? And if line 1 and line 2 have an intersections, have a point of intersections, then which means that the value, both this parametric, should be equal. Okay. So let make those assumptions. So make it equal, so we can take each component, 1 plus t equal to s, minus 2 plus 3t equal 3 plus s, and 4 minus t is minus 3 plus 4s. Okay, if we solve the first two equations, let's solve these two equations. Okay, we can have this is let's multiply by 3. So 3 plus 3t plus 6s. Let's subtract. This is 5. This is 5s -3 plus 5s. So s will be 8 over 5. So 1 plus t is 16 over 5. So t will be 11 over 5. Okay. So this is the first one. But when we solve the second and third, let's solve this. Multiply by 3 for the second one. So 3 multiply by 3 multiply by 3, and we add both sides. So adding this, 12, 10, -6 plus 13s. And the s already different, not the same. And this suggests that L1 and L2 are skew lines. So first, to check whether it's skew or not, first check whether it's parallel. Second, check the point of intersections. Okay, if they have the same point of intersections. I hope today we'll finish the line and maybe some of the plane. So this is line. So line finish here for vectors in an equation of line. The next part after this, we will have the equation of plane, and we will have a short break. Okay, we will have this. Okay, the next topic is, so this is line. Okay. The next topic will be about the planes. So how to describe plane on a space? So plane on space. How to describe in terms of some vectors, some positions. Okay. If we describing the positions like in line, for example, we have A and we have B, and from both cases we can describe the vectors, right? The vectors, let's say this is R0, like we did before, and this will be the R. And we have some shifting positions that can be described as a vector as well. We describe at the beginning as A, right? So of course, if we have line, so the line that is in the direction of A, we can describe easily in a space, right? With these 2 points, each has vector positions, and we can describe line very easily. Okay. Now, how to describe the plane, which means that if I have, like for example, this line, obviously it is lie on the invisible plane, right? If I can draw my plane here, for example, this is the plane. Okay. So the plane here is obviously where this vector A or the line A will be, right? And then how to describe the plane? If we just looking at the line, then we will not going anywhere, right? It's difficult to describe the plane through this line. But if for example we have another vector that is, let's say, perpendicular. Okay. So if this line or if this plane is looking like this, then I will have another segment of the vector that is perpendicular, and we can define this vector as n, which is the vectors that is perpendicular to the plane. We call these vectors also with the name normal. Okay, let me put some graph to make it more more easy to be looking at. Okay. But I say this is the line that we have discussed previously, right? R0, the initial point, and then the point directions. We have the line here. And if we define that there is a perpendicular vector, which is n, the normal, we call it normal vector, then we can specify what will happen if we have the perpendicular. If you remember the vectors on, I think before we have the holiday, then we can set up, if we have n, if we dot with the line, which is r minus r0, this should be equal to 0. Because you remember the dot product, the cosine should be 0, which is the 90 degree, right? Okay. So we can have this equation, or we can rewrite this in terms of, okay, now both of these equations we call the vector equations of plane. So we start from this two particular equations, or from the fact that in the dot product, when you have perpendicular or orthogonal, you will have the cosine to be 90 degree. So you will have a 0 value. And from these equations, we can set up a component for each n and each position vector with some definitions. So we set up the definitions for the n. So the component n, let's say we have the directions A, B, and C. And let's say the R will have X, Y, Z. And R0 will be X0, Y0, and Z0. Then we can set up our dot multiplications or dot product. And this will be equal to 0. Okay, if we multiply using the dot product, then we will have A x minus x0 plus B y minus y0 and plus C z minus z0 is equal 0. Now this is what we call the scalar equation of the plane. So as long as you get the directions for the normal, and you know the initial point for the vectors, then you can set up these equations. Okay, I hope you can observe how we can deal with, or how can we get this equations. And this equation come from the dot product. The dot from the line segment or the line vectors, we are multiplying within the dot product with the orthogonal vector or the normal vector. Now another form that we can set up from these equations, for example, if somehow we can have some numbers and we can simplify this equation. This equation can be written as the ax plus by plus cz plus d equals 0. Now this is called the linear equations of plane. Okay, let's take some example. Start from very simple questions. Find equations of the plane through with normal vector find the intercept and sketch the plane. Now this point will be the initial point, the x0, y0, and z0. This n is our directions, A, B, and C. So we can just take this into our formula. Now we will have the 2x minus 2 plus 3 y minus 4 plus 4 z minus, so we have plus 1 equals 0. Solve this equations. 2x plus 3y plus 4z is equal negative 4, 12, negative 12. And to find the intercept, x-intercept, this is where y equals z equals 0. So x will be equal 6. Y-intercept, this is when x equals z equals 0. This is y will be 4. And the same with z. So z will be equal to 3. So drawing all this tree, one, two, three, 1, 2, 3, 4, 5, 6. Okay, and that's our plane. Okay, let me give you another example. Find equation of plane that passes through point P 1, 3, 2, point Q, and R, Okay, find equation of plane that pass through all these 3 points. So the idea behind of this question is first we need to decide our vectors. We can have vectors from P to Q and then Q to R, at least two vectors. And from those 2 vectors, we can decide how we can get the normal vector. So we can get the normal vectors through the cross product. So first, define the vectors from this point, and from those points, or from those vectors, we can define the normal vectors that is orthogonal through the plane. Okay. So first, define the vectors. Let's say PQ and PR. Okay. So PQ we will define as 3 minus 1, 2, minus 1 minus 3 is negative 4, 6 minus 2 is 4. Okay. And PR is 4 minus 1 and minus 2. Since this PQ and PR, they both in the same plane, okay, then the cross product from these 2 vectors will resulting the normal vectors, right? So we can define the normal vectors as PQ crossing the PR. So we can set up I, J, K, 2, negative 4, 4, 4, negative 1, negative 2. I will just using the multiplication for cross product. So 2, 4, negative 4, negative 1. So multiplication. So 8i plus 16j minus 2k. And minus 16k oh, it's plus, just plus, because I already take the negative. So 16 oh wait, it's correct. negative 4. Oh yeah, it's correct. So 12i plus 20 and then 16 minus 2 is 14. Okay, so this is the normal vectors. Okay, when P is this point with normal vector n, then the equation of plane will be 12x minus 1 plus 20 y minus 3 plus 14 z minus 2. We can divide by 2, I think. 6, 10, 7. So we will have 6x plus 10y plus 7z. And then we will have negative 6, negative 30, 36, 14, 50. So this will be negative 50. Move to right side, it's 50. So this is the equation of plane. And now similar to what's happened with the line. So in the plane, we will have also the same keywords, which is the planes can have parallel or maybe intersection. So the plane is parallel, or maybe they have intersection between the plane, or maybe skew. Same keywords with lines. So if you have several lines, you'll have parallel, intersections, and skew. The planes also having the same keywords. But then in plane, how we can make, or how can we know whether they are parallel or intersections? The difference is we know from the normal vectors. We know from the normal vectors. If we have, for example, line or plane that has the, let's say it's parallel, they have the same normal vectors, the same directions, right? So we can observe from the normal vectors. And if they have the intersections, the normal vectors will also intersect. The vectors will also intersect. Okay. So let me give you an idea on how we can look on these intersections. Okay. Example. Find a point at which line with parametric x now in this example, the intersection is between line and plane, and it's okay. Intersect the plane so meaning, so assume that this is true, and the parametric or the line will be intersecting the plane, which means that they need to be equal. At some point they need to be equal. So we can equaling this parametric with this plane. So we can exchange this x with the parametric. And we are looking on how we can know or when the plane and the line will be intersecting. Okay. So first we substitute the parameter. So for two plus 3t plus 5. Oh, minus, sorry. Okay, we simplify this. We solve this. Let me solve this. -12, -8, -10. So -10t. 8 minus 10 minus 2 is equal 20. So t will be -2. So they both, line and plane, they intersect at, so intersecting at t equal -2. And if we need to find the point in which this question is asking the point, then we can exchange from the parametric. So when t equal -2, then x equal 2 plus 3 -2, -4. So the point is -4, 8, and 3. Okay, some notes for this intersections. Two planes we call parallel if their normal vectors are parallel. If not, then probably they intersect in a straight line and the angle between two planes defined as acute angle between their normal. Like this one. And sometimes if you want to know how we can find the angle, we can take the dot product. The dot product of n1 and n2, the normal vector 1, normal vector 2, the dot product, and you will find the cosine theta, and you can eventually get the angle. Okay. Okay. Well, let me finish the sections with the last one for the plane, which is the distance. Okay, to find distance. Okay, so if we have the plane, for example, the plane. So if this is the plane, and let's set up some vectors. And we have normal, maybe normal here. The normal vectors. And that this is becoming a 90 degree. Okay. And let the vectors from P0 to P1 becomes vector B. Now, if we define from the plane to P1, we have some certain distance, right? So we define this, let's define this as our distance, D. So D is a distance. Okay. Let the P0 be the point x0, y0, z0, p1, x1, y1, z1. Then the vector b we can write as x1 minus x0. If you remember, this distance is actually similar to what we have done in the previous section on the dot product, in which we can have the projections, the vector projections. We can project the vectors. So D is equal to absolute value of scalar projection of B onto the normal vectors. So D, we can write this is as a projections or scalar projections of vector B to vector N. Or in this case, this will be the N dot B defined with this N. We need to take the absolute value because we are dealing with the distance. It should be a positive number, right? And for N is, let's say, ABC. So let's dot product the N with B. Okay. So this will be A x1 plus B plus C and the magnitude value of n is b squared plus a squared, b squared, and c squared. We can write this as, let me just write ax1 plus by1 plus cz1 plus or minus, sorry, and since P0 lies in the plane, so the coordinate will satisfy the plane. So we have x0 plus b y0 plus c z0 plus d will be equal 0. Then we will have the formula that the distance will be a x1 plus b y1 plus c z1 plus d. So this means that this is the distance. Okay, this is the distance from P1 to plane ax plus by plus cz plus d equals 0. Okay, and don't forget we'll have midterm on 19, right? 19 Tuesday. Okay. Topics will be just chapter 10 and 11. Okay. However, for the chapter 12 and chapter 13, I will give you in the quiz. Okay, in the quiz. So after we finish this, still have one more sections on chapter 12, and after that we'll move to chapter 13. Before chapter 13, I think some part at the beginning I will give you as additional video. I hope you can watch first before lectures. Probably this week I will prepare, and we need to watch it before we enter class. But actually, chapter 13, the half of chapter 13 is basically just mentioning how we can set up the vectors and how we can use some calculus techniques such as derivatives, integration. So if you already familiar with the calculus 1 techniques, just a regular technique, then it should be okay. The difference is we are writing all those calculus in terms of vectors. That's the difference. Okay, I think I can move to the last sections on chapter 12. Just an intro for next Tuesday. So this is the plane, the distance and planes. Okay. So this is 12.6 quadratic surfaces. Okay, what is quadratic surfaces? Before we learn quadratic surfaces, we first deal with the cylinders. Okay, let's start with z equal x squared. If we have this z equal x squared, of course, if we are looking on 2 dimensions, just one side from the z and x, the axis is just 2, we will have just a quadratic regular parabola. But if we draw in terms of 3 dimensions, because there is not mentioning any y here, which means on y-axis, these 2 terms will be all over the place of y-axis, which means if we draw this, let's say this is z, this is x, this is y. Okay, we can imagine z and x easily, just like this, right? So let me just draw that first. Okay. This is when it is at the origin, or if we look on y, this is at y equals 0, right? If we move y maybe to 1, 2, 3, because we just set up the z equal x squared, so this quadratic equations will be all over the place on y. So we can have, let's say maybe here, we also have this quadratic one. Maybe here, we also have. And also, if we take the negative part, this is also having the same. Okay. And if we connect all this curve, we connect into some surface, okay, and it's becoming a surface. So let me just draw with the green. So we will have some surface here. Okay. We call this a cylinder. To be precise, this is called a parabolic cylinder. Okay, parabolic cylinder. So cylinder, as a definition, if I write some definition of cylinder, this is a surface consists of all lines that are parallel to the given line and pass through given curve. And if you look here, have a line that is all parallel. Okay. And this is parallel to the y-axis. And same way, if we have x squared plus y squared equal 1, we can think this as a circle. But in terms of 3 dimensions, it's become a tubular or a cylinder. Right? Or maybe another circle. It's the same shape but different directions. Right? So this will be like this, and this will be probably like this. I think this is just the introductions for the intro. So we will going further next